In computer networks, we are taking chapter number 2, the physical layer. Wireless transmission. Wireless means there will be no wire, fiber optic, coaxial, twisted, nothing. Transmission means sending and receiving the data, information, bits, waveforms. So if running a fiber or a cable, say from a building to some place to a place where the terrain is difficult, undulated terrain, mountains, jungles, swamps, the wireless is the best idea. The best appropriate way of communication or transmission is wireless. Now this all started, actually the modern wireless digital communication, it all started with a research project, and it was done by a Professor Norman Abramson of the University of Hawaii in the 1970s. The electromagnetic spectrum. So electromagnetic spectrum is total frequency range. Every frequency range has some use to humankind. All it started with the electron. When the electron moves, it creates an electromagnetic waves. Whenever it is in motion, it creates certain waves called as electromagnetic waves, because the electric and magnetic waves are perpendicular to each other and they can propagate through the space, even in the vacuum. Now here is a great name, James Clerk Maxwell. Now he was the first British, not the first British, but the first person. He was a British physicist, and he was the first to predict these electromagnetic waves in 1865. Then came the German physicist Heinrich Hertz. He observed it first. So predicted by Maxwell, observed by Hertz in 1887. So whenever we talk about electromagnetic wave, oscillation, wave, harmonic, there are certain physical concept or terminology. So the number of oscillation per second, if I take 1 second, this is 1 second periods. This is the wave, there is another wave. So the number of oscillation per second of a wave is frequency. This frequency is measured in hertz. Hertz, because of the great name Heinrich Hertz. Now wavelength is the distance between two consecutive maximum, minimum, maxima, minima, and this is designated by, or this is shown by, written by Greek letter lambda, lambda. So let me just give you more idea about it. This is the wave and this is the direction of propagation. Just assume a center line through which it propagates. Now these are the oscillations, and as I said, there is electromagnetic. So electric and magnetic are perpendicular. So these are the oscillations. The upper part is called as crest. The lower part is called as trough. The distance between the two crests or the two troughs are wavelength. So this is the imaginary center line. The highest it goes, or the lowest it goes, the distance between the center line and the peak point above and below, that is called as amplitude of the wave. Amplitude. Frequency is the number of oscillations per second. We can also call it as wave cycle passing a given point in a given period of time. So these are terminologies that we will be using without any definition, so you need to understand it. Then the speed of light in the vacuum is 3 into 10 to the power 8 meter per second. Okay, all this discussed. If you have the electron moving, electromagnetic waves can be produced. So why not to attach an antenna? So an antenna which is attached to this electrical circuit, these electromagnetic waves, they can be sent and received, that is broadcast and received by the receiver. The sender can send, receiver can receive these electromagnetic waves are the basis of all the radio communication. So in vacuum, all electromagnetic waves of any frequency, they travel at the same speed as I just mentioned. It is speed of light represented by c, 3 into 10 to the power 8 meter per second. 3 into 10 to the power 5 kilometer per second, or 1/4 or 30 centimeter per nanosecond. But when this electromagnetic waves, it goes through or travels through copper or a fiber, the speed becomes 2/3, 2 by 3 multiple. So here we have the electromagnetic spectrum. The fundamental relation of this electromagnetic spectrum used widely is C equals lambda into F. Sometimes F is also called as nu. So what all you see here? Here is lambda. Lambda is the wavelength, the distance between the crest or the trough. Frequency, number of oscillations per second. C, speed of light. In vacuum we are right now talking about. So this C equals lambda F. So C is a constant. So lambda, that is the wavelength, and frequency are inversely related. Whenever, as a rule of thumb, we take lambda in meters or the wavelength in meters, the frequency will be taken in megahertz. Lambda into F will be then 300. For example, the 3 meter long wave will be 100 megahertz waves. That is, 100 megahertz wave will be 3 meter long. That is the wavelength I'm talking about. While if you go to 1000 megahertz, the wavelength will be 0.3 meters. 3000 megahertz, 0.1 meters. High frequency, low frequency, this is how it is defined. That is, high frequency is per second if the wave is long. If the wave is long, that is low frequency. Number of oscillations per second are very less. So the wavelength has to be higher. That is, the wave, if frequency is less, lambda will be higher because they are inversely proportional because C is the constant. And similarly, if the frequency is higher, the wavelength has to be less, small. This is the relationship. In electromagnetic spectrum, there are different range, there are different hertz, there are different wavelength, there are different ways we use it. Okay, there will be different nature of wave because one will be higher wavelength, one will be lower wavelength, and consequently the frequency. So if you see here, we have the radio waves. Radio waves, the wavelength is of the order of a soccer field. See, then we have microwaves, infrared, visible. Visible is very small. Ultraviolet, X-rays, gamma rays. So this radio waves we use for the AM radio, then it comes FM radio, then we have the different ways, for medical purposes we use X-rays, and there are radioactive elements, the radioactive work done in the gamma rays electromagnetic range. So the radio, microwave, infrared, visible light portion of the electromagnetic spectrum, they all can be used for transmitting the data, information. How? By modulating the amplitude, frequency and phase. We call it as amplitude modulation, frequency modulation and phase modulation. We'll talk about that. The ultraviolet rays, the X-rays, the gamma rays, they are having high frequencies. The wavelength is very small, very sharp they are. They are very difficult to produce. Even the modulation is very difficult, and they do not propagate well through the buildings. So they have their own use, but they are dangerous for the living being. If X-ray person, he himself is out of the room when he takes the X-ray if you go for the X-ray. That is how much it is difficult for the living being. Even the gamma rays, the ultraviolet rays, we have all the sunscreen for that. So the ITU, International Telecommunication Union, the names they have given earlier, that is the LF, the low frequency, It goes from 1 kilometer to 10 kilometer. This is the frequency range I'm talking about. And this frequency range is 30 kilohertz to 300 kilohertz. Then we have this LF for low frequency, MF for medium frequency, H for high frequency. No one was thinking at that time that the higher frequency will be used for the communication purposes. So then came the higher bands like the VHF, very high frequency band, then ultra high frequency, super high frequency, extremely high frequency, tremendously high frequency. These were there. Frequency hopping spread spectrum. So the name is suggesting frequency will hop, will jump, will change from one frequency to another. And the spread spectrum is using all the frequency range, spreading it. So in frequency hopped spread spectrum, a transmitter hops the frequency, changes the frequency, jumps the frequency from frequency to frequency hundreds of times per second, as you see in the picture also. And it is quite popular in military communication. So if I'll just take a time, for example, 625 microseconds, just giving you an idea that this is the time and the change of frequency time. So as I said, they are very popular in the military use, military communication, because the frequency is hopping, changing. If one frequency is used, it can be found. But if you are jumping through the frequency, hard to detect and almost impossible to jam the signal, stop the signal or destroy the signal. And because it is changing, it offers very good resistance to fading. As the signals, they may take different paths also. Different paths, different signals. That is, the fading is less. Multi-path fading you can talk about. And because I said this, say, if particular frequency is affected by a certain thing, maybe for jamming, or maybe it is absorbed by rain, for example. Now that particular frequency will remain unused, but because the frequency is jumping, that particular frequency will be only affected, other frequency won't be affected. So it also offers resistance to narrowband interference, as receiver will not be stuck on an impaired frequency for long because it is jumping. Now you see a very beautiful woman. You must appreciate her beauty and her brain also. Why I am saying that? Because she is not only the actress, she is the inventor. First, let me tell you, this frequency hopping spread spectrum, this technique is also used commercially in Bluetooth, in the older version of wireless LAN, Wi-Fi 802.11. So this technique was co-invented by the Austrian-born film star Hedy Lamarr, or the birth name Hedwig Coaxial. She was responsible for the development or invention of this. The story about her is her first husband. He was actually the armaments or arm manufacturer. And because they were in love, so she told him that, how do we block the radio signals? And these radio signals were actually blocked because it was used at then for controlling the torpedoes. Now, it is underwater I'm talking about. Now, when she came to know this, she got very, very horrified, because when she came to know that his husband is selling the weapons to Hitler, she was horrified. And then she just left. She fled, disguising as a maid, came to Hollywood, and then she became famous movie actress Hedy Lamarr. Okay. Now she invented frequency hopping to help, and she actually helped the Allied war effort. Everyone against Hitler, allied. Direct sequence spread spectrum. Now you see here, this is the user information data. There is a code that is called a spreading code, and finally, if you combine them, you get the spreaded information. So direct sequence spread spectrum, it uses code sequence. It uses code sequence there are multiple people, say for example, they have different code, and this code sequence they use to spread the data signal over a wide frequency band, and this is quite used commercially, and this is a very good spectrally efficient way to let the multiple signals they can share the same frequency band. So signals, they are given different codes. For example, one has been given one codes, other has been given two codes. We'll talk about this code division multiple access in detail. Right now it is just a code division multiple access. So the 3G mobile telephone networks, when they came, this forms CDMA forms the basis. GPS also it is used. The GPS signals are on CDMA, and because of this, because we have multiple code, so it can tolerate interference and fading because only a fraction of desired signal is lost. Ultra wide band communication. So I told you about frequency hopping, then the other one which we're using the CDMA, then we have the ultra wide band. This is the underlying. You see, all these are working here. There is underlying figure. So ultra wide band, the name suggests this kind of communication. It sends a series of low energy rapid pulses, and at the same time changing or varying their carrier frequency. This carrier frequencies is changed to communicate information. Okay, so the UWB, you can define it as a signal that have a bandwidth of at least 500 megahertz. 500 megahertz. Or if you take the frequency band, this center frequency you take, it should be at least 20% of the central frequency. So with this bandwidth, this UWB or ultra wide band, this has a great potential to communicate hundreds and hundreds megabits of data per second. This is how it works. It can tolerate strong interference from other narrowband signals, and UWB, it doesn't interfere with the carrier signals in the same frequency band. This is the whole concept here. And this can also be used in imaging through the solid objects. Why? Because it passes through it ground, walls and bodies, and also it can be used as a part of a precise location system. That is why, because it is going through solid objects, and that is why it is used as for imaging, precision radar imaging and precise location systems, so location tracking technologies. So ultra wide band, secure, accurate, reliable, real time, low energy. So these are the properties of this UWB. Coexistence also. Okay, using the spectrum for transmission, radio transmission, this we are going to see in the next discussion. Till then, thank you so much. Take care of yourself.